Hello, today we are going to learn about a very interesting data structure problem called MinStack. The challenge is to design a stack that can return the minimum element in O of one time. Let's see how we can solve this. So what exactly do we need to build? We need a stack that supports 4 operations: push to add an element, pop to remove the top element, top to see the top element, and getMin to get the minimum element. And here's the catch. All operations must run in O of one constant time. Now the naive approach would be to scan the entire stack every time we call getMin, but that would take O of n time, which is not acceptable. We need something smarter. One popular solution is the two-stack approach. The idea is simple. We maintain an extra stack to keep track of the minimum values. Let me show you how it works. Here we have 2 stacks, the main stack on the left and the min stack on the right. The main stack stores our actual elements, and the min stack keeps track of the minimum at each level. Let's push 5 into our stack. Since this is the first element, 5 goes into the main stack, and 5 also goes into the min stack because it's our current minimum. Now we push 3. 3 is less than 5, so we have a new minimum. We add 3 to the main stack, and we also add 3 to the min stack because it's smaller than the previous minimum. Next we push 7. 7 is greater than our current minimum 3, so it just goes into the main stack. But notice, we still add 3 to the min stack to maintain the same size. This way, each position in main stack has a corresponding minimum. Now push 1. 1 is less than 3, so we have a new minimum. Both stacks get updated. 1 goes into main stack and 1 goes into min stack. Let's call getMin. We simply peek at the top of our min stack and we get 1. That's our minimum. This is O of 1 because we're just looking at the top element. Now let's do a pop. We remove from both stacks. The main stack returns 1, and we also remove 1 from the min stack. Simple, right? If we call getMin now, we get 3. See how the minimum updated automatically? That's the beauty of this approach. Let's pop again. We remove 7 from main stack and 3 from min stack. Both stacks stay synchronized. And getMin now returns 3. The solution works perfectly. So our 2-stack solution works great. All operations are O of 1. But there's one problem. We are using O of n extra space for the min stack. Can we do better? Yes, the space complexity is O of n, which means if we have 1 million elements, we need another million spaces for the min stack. Let's see if we can reduce this to O of 1 space. Here comes the clever part, the O of 1 space solution. Instead of using extra space, we will encode the minimum information mathematically inside our stack itself. Here's the magic formula. When pushing a new minimum, instead of storing the actual value, we store 2 times value minus current min. This encoded value will always be less than the new minimum, so we can detect it later. And when popping, if top is less than min, we restore the previous minimum using 2 times min minus top. Beautiful, isn't it? Let's see this in action. We have a single stack now, no extra space needed. We just maintain one variable for the current minimum. Push 5. This is our first element, so we store 5 as it is, and minimum becomes 5. Simple start. Now push 3. 3 is less than 5, so it's a new minimum. We need to encode it. The formula gives us 2 times 3 minus 5 equals 1. So we store 1 in the stack, but our minimum becomes 3. Push 7. 7 is greater than or equal to our minimum 3, so we store it normally. No encoding needed here. Push 1. 1 is less than 3, new minimum alert. We encode 2 times 1 minus 3 equals minus 1. We store minus 1 in the stack and minimum becomes 1. Notice how minus 1 is less than 1. That's how we'll detect it's encoded. getMin simply returns our min variable, which is 1. O of 1 time, O of 1 space. Perfect. Now top is interesting. The stored value is minus 1, which is less than min 1. This means it's encoded. So we return the actual value, which is our current min equals 1. Smart, right? Pop time. The top is minus 1, which is less than min 1. Encoded value detected. We return the actual value 1 and restore previous min. 2 times 1 minus minus 1 equals 3. Our minimum is back to 3. And getMin now correctly returns 3. The formula worked perfectly. Let's test an edge case. What if all elements are in descending order? Every push will create a new minimum. Fresh start, empty stack, no minimum yet. Push 10, first element, stored as is, minimum is 10. Push 8. 8 is less than 10, so we encode 2 times 8 minus 10 equals 6. Store 6, min becomes 8. Push 5. 5 is less than 8. Encode again. 2 times 5 minus 8 equals 2. Store 2, min becomes 5. Push 2. 2 is less than 5. 2 times 2 minus 5 equals minus 1. Store minus 1, min becomes 2. Look at the stack. It has encoded values shown in red. Get min returns 2. Correct. Pop. Top is minus 1, less than min 2. Encoded. Return 2. Restore min. 2 times 2 minus minus 1 equals 5. Pop again. Top is 2, less than min 5. Encoded. Return 5. Restore min. 2 times 5 minus 2 equals 8. Get min returns 8. Even with all descending values, our algorithm handles it perfectly. Another edge case. Duplicate values. What happens when the new value equals the current minimum? Empty stack ready for duplicates test. Push 3. First element, min is 3. Push 3 again. Now 3 is equal to minute 3, not less than. So we store it normally, no encoding. This is important. We only encode when strictly less than. Push another 3. Same logic. 3 equals 3, no encoding. All 3 elements stored as 3. Get min returns 3. Correct. Pop. Top is 3, which is not less than min 3. Normal pop returns 3. Pop again. Same thing. Normal pop returns 3. Get min still returns 3. Duplicates handled correctly. Final edge case. Negative numbers. Does our formula work with negatives? Let's find out. Starting fresh for negative numbers test. Push 2. First element, positive number. Min is 2. Push minus 3. Minus 3 is less than 2. New minimum. Encode. 2 times minus 3 minus 2 equals minus 8. Store minus 8. Min becomes minus 3. Push 0. 0 is greater than minus 3, so normal push. Store 0 as is. Push minus 5. Minus 5 is less than minus 3. New minimum. Encode. 2 times minus 5 minus minus 3 equals minus 7. Store minus 7. Min becomes minus 5. Get min returns minus 5. Negative minimum. Working perfectly. Top. Stored value is minus 7, which is less than min minus 5. Encoded. Return actual value equals minus 5. Pop. Top minus 7 is less than min minus 5. Encoded. Return minus 5. Restore. 2 times minus 5 minus minus 7 equals minus 3. Pop normal value 0. Returns 0. Get min returns minus 3 kilocomart. Even with negative numbers, everything works beautifully. And we are done. We have successfully implemented a MinStack with O of 1 time for all operations and O of 1 space complexity. Let's recap the key formulas. For push, when value is less than min, store 2 times value minus min. For pop, when top is less than min, restore min as 2 times min minus top. And get min always returns min in O of 1. This is a very popular interview question, so practice it well. Thank you for watching and happy coding.